All right, as mentioned, I have a practice problem for the third and final video today, which is to predict the pressure and compositions for the vapor-liquid-liquid equilibrium of methanol cyclohexane at 308 Kelvin. So as I mentioned in the video about the modeling, I have 5 unknowns, and I need to specify one of them by Gibbs phase rule in order to set the other ones. So what are my unknowns that I want to calculate? I want to know what the pressure is. I know what the temperature is, so I'm going to actually start with temperature. Pressure. T is 308 Kelvin. Pressure is an unknown. It's going to be in bar. I have my X1 from phase 1 composition, my X1 of phase 2 composition, and my Y1. Okay, so these are my 4 unknowns. And I want to solve those 4 unknowns by solving these 4 equations. So how would I go about doing that in Excel? Remember that I need a good initial guess for all of these. So I'm going to go ahead and guess 1 bar. I'm just going to put in 0.5, 0.5, and 0.5. So I'm going to make the point later that, remember, you need to have a good initial guess. You can't just make any old initial guess. So we're going to see what happens when we try to solve this system of equations. All right, and I don't think I don't need to go through and solve this for many different compositions. There is one unique answer here. So I'm not drawing the diagram. All I want to know is what these 4 variables are. So I'm going to highlight them as these are my unknowns that I want to solve for. So really all I have to do is set up a solver with these 4 equations in order to get it done. So my equation 1, equation 2, equation 3, and equation 4. My plan is to just go equation by equation, and whenever I need to calculate something in the interim, I'll tackle that when the time comes. Or actually, I'm going to get to the first equation and see I have a gamma 1 from phase 1, so actually I have to figure that out relatively soon. So I'm going to shift this down a little bit. How many things am I going to have to calculate? I'm going to want gamma 1 from phase 1. I want gamma 1 from phase 2. And I'm going to want gamma 2 from phase 1 and gamma 2 from phase 2. I'm going to need all 4 of those. So the problem statement tells me to use the 1-parameter Margulies model. Remember that the Margulies model for the activity coefficient is ln of gamma is equal to a times x squared, where gamma 1 takes x2 squared and gamma 2 takes x1 squared. So I have a value for the Margulies A, so I can go ahead and calculate those, right? So because it's ln of gamma, I need the exponent of the parameter A times, let's see. So if I want to do gamma 1 from phase 1, I'm going to need the liquid composition of component 2 in phase 1. So this is going to be 1 minus x1 of 1, right? Because it's x2 from phase 2 is my equation. I didn't clip it from my notebook, but go back in your notes where I have the 1-parameter Margulies equation. ln of gamma 1 is equal to a times x2 squared. Also, don't get confused by the superscript Roman numeral 2, which denotes phase 2 and squared. So if I were to write the equation, you have to think about that quickly. And it's not, I need the caret there to raise it to the power 2. Okay, gamma in that range is acceptable. ln of gamma 2 for phase 2 is similarly equals exponent of a times 1 minus x1 from phase 2 squared. And I forgot to close out my parentheses, so accept that correction. Gamma 2 from phase 1 is equal to exponent of a times x1 from phase 1 square, and gamma 2 of the liquid is equal to exponent a times x2 squared. And these are all going to be the same because I've made an initial guess that was not very smart. Remember, when I have a liquid-liquid equilibrium, I always have two liquid phases. And if I guess the same number for the two liquid phases, then I don't actually have two different phases. I have the same phase. So this is why I made that point if you need a good first initial guess, because look, when I come to my equation 1, right, I'm going to want this equation to be 0. So if I say it's x1 from the liquid times gamma 1 for phase 1 minus x1 from phase 2 times gamma 1 from phase 2, it's going to be 0 just by default. So I'm really not solving for anything. And if I guess anything that's too close, then solver is going to just give me this trivial solution. So I need to make a better initial guess. And I've been assuming that phase 1 is going to be rich in component 1. So when I'm guessing what my x1 from component 1 is, I'm going to want to bump it up a little bit. So I'm going to guess 0.9 and 0.1. Just completely arbitrarily, remember, I don't actually know what any of these are. I'm just making a good first initial guess. My y1 guess, I think, can stay at this point. All right, that's my equation 1. Remember, I'm going to want to use solver to set all these equal to 0. So equation 2 is 1 minus x1. And I wrote it like that because this is x2 from phase 1. So this is easy just to import into Excel. Times gamma 2 from phase 1 minus 1 minus x1 2 times gamma 2 from phase 2. All right, perfect. Moving along to equation 3 is equal to y times p. And my p is in bar and my vapor pressures are in bar. So that means my units are going to be dimensionally consistent, which is good. That's what I want. Minus x1 from phase 1 times gamma 1 from phase 1 times p set for component 1, which is methanol. And I don't have to dollar sign it because I'm not dragging the formulas down, but it's good habit. I guess I didn't do that, or I did do that here, right? I'm always dollar signing my Margulies A. And equation 4 is equals 1 minus y1 times p minus 1 minus x1 of phase 2 times gamma 2 from phase 2 times the vapor pressure of component 2. All right, so let's go ahead and set up solver. So hit up data, solver. I want to set my objective B19, that's my equation 1, to a value of 0 by changing these 4 variable cells and subject to the constraints. Oops, not change. I want to add the constraint that these 3 equations are all equal to 0 as well. And uncheck this box and let's see what happens. All right, it found an initial answer. Let's double check and see that it makes sense. And just by looking at it, there's nothing that tips me off that indicates to me that anything is wrong, right? So I have different compositions for x1 from phase 1 and x1 from phase 2. So I have different compositions of the liquid phase, which is good. I kind of intuitively know by looking at that phase diagram that I drew that the vapor phase composition should be in between the liquid phase compositions. That's also true. And I have a low pressure, right? I have 0.427 bar, which means that my vapor phase is likely ideal, right? It's about a half an atmosphere, a little bit less than that even. So the ideal phase is appropriate here. I have all of my equations that are 0 or very, very close to 0. 5 times 10 to the 8th is pretty low. And I also have symmetry in my gammas, which is expected because I'm using the 1-parameter Margulies model. So therefore, I would say this problem is solved. And just to be complete about how I answer the problem, I would say that the pressure is 0.428 bar. I would say the compositions of the vapor phase is, let's see, 58%, 58.0% of component 1, which is methanol, which means the other 42%, 42.0% is cyclohexane. I would say liquid phase 1 is 84.9% methanol, and the other 15.1% cyclohexane. And liquid phase 2 is then 15.1% methanol, and the other 84.9% cyclohexane. Also recognize that I have symmetry here as well, right? So I have the compositions of the liquid phases are the same, but they're just flipped, and that reflects the fact that I'm using one parameter Margulies instead of two parameter Margulies. So again, that is how you solve a prediction vapor-liquid-liquid equilibrium problem, a system of 4 equations and 4 unknowns.